All right. So this is the first step of, how neurons represent the world. They translate everything around you into membrane voltages. And then they do something with those membrane voltages in order to combine information across all sorts of different things. Again, we'll look at this when we look at different types of sensory organs and processing and so on. All right. So this is here really this again. The presence of physical or chemical signals is encoded as a change in the membrane potential, the voltage across the cell's membrane. Important idea. Now, of course, the thing is, here I've got a cell membrane. It's at rest. Potassium is leaked out. It's positively charged on the outside, negative on the inside. Here I've got a place where I've got my stretch receptor. Okay, the stretch receptor lets sodium in. Suddenly I've got positive charge here. Of course, that positive charge is going to be attracted to these negative charges, and my sodium is going to flow along here, and I'm going to have an electric current that will carry this signal along. So this signal will automatically, that's just encoded my sensory thing in the world, will automatically spread along those tubes, these neurites. Okay, and like this will actually give you, like this you can imagine that you can carry these signals through the neurons, but you can't carry it very well. All right. The reason for this is that, of course, you'll start to get leakage going back out because the potassium channels that set up this voltage in the first place are still open, and you get positive charge rushing in, it'll just push out more positive charge. Okay. So the idea is that if you inject a current into a neuron in a particular place, meaning you're allowing positive charges in, they'll just leak out, and your electrical signal will get lost over a distance of only a few millimeters. Now, some neurons in your brain, in your body, are 2 meters long. All right, because they have to tell information from your big toe to your noodle. All right, so over those 2 meters, they can't carry the signal just by having the ions flow along these long neurites. They have to have a trick, and the trick that they have a trick because you get leakage. Okay, you get leakage through potassium resting channels. You basically have a sodium that's been allowed in order to send the signal. It pushes out another potassium through the thing again, out through its resting channel, and then basically you're losing positive charge. And you also get so-called capacitive leakage, which really you don't need to worry about. But basically, if you've got, imagine you've got a cell that is polarized in its resting state. A sodium comes along here, snuggles up to this negatively charged organic anion. Suddenly, this positive ion, positive potassium ion, which has been sort of attracted to this sodium ion and is sort of, ogling at it, with, longingly, suddenly feels the, repellent positive charge here and wanders off. All right, and it will have the effect as if a positive charge had traveled through here, even though it's of course not the same positive charge. But you end up with a loss of. Okay, so what you do, you somehow need to need to make sure that these currents can keep flowing. Well, you have to renew them, and the way you renew them is that you've got so-called voltage-gated sodium channels in your in certain parts of your neuron, okay, and they send up so-called nerve impulses. I don't know whether you've ever, if you've heard of nerve impulses. All right, so we can encode things in our neurons initially through just changing the membrane voltage of the neurons, but we can, but we need to, in order to carry signals over long distances, we need to set up nerve impulses by having voltage-gated channels that will renew the current. Okay, so the idea is I've got. What happens is that if I depolarize the membrane in which one of those voltage-gated channels sits, then this channel will open and allow more sodium in. All right, so I've got sodium that goes in because I've been stretched. All right, the sodium flows in, it depolarizes the cell, that opens these channels, which allows more sodium in. They travel along and go to the next channel and allow yet more sodium in, and so on until the cell is completely depolarized. Okay, so the cell goes from being negatively, having a negative polarity to having a positive polarity in a positive feedback circuit. The thing is, like this, just by making the an inflow of current cause yet more inflows of current, and so on, I can renew the current on every new part of the neural cable, all right, and send it along for long distances. The disadvantage is that this will, of course, carry on until all the channels are open. So I can no longer send a small signal by depolarizing the membrane only a little bit. Okay, the neuron will fire an impulse because it's depolarized enough to set off the first one of these, and then I get a feedback process that will just open them all, or it won't. Okay, so when that, when these sodium channels open, we say the neuron fires an action potential, which is just a Ponzi word for nerve impulse. Okay, so nerves have to decide whether they want to fire impulses or not, and they encode. So these nerve impulses will basically carry information for very long distances, but they we can no longer encode signals by just saying, I'm going to depolarize a little bit or not, but I can basically depolarize. I can have an impulse rarely, or can have it very often. So these sodium channels, they'll open up. Of course, if they just stay up, then the neuron would just go to a different potential and they would stay there forever. But what happens is that after just a fraction of a millisecond, they slam shut again, and they let the cell return. So if you measure this membrane, and if you measure its potential, and you cause an action potential, you depolarize it a bit, okay? It will depolarize until it's changed its polarity all the way around, and then these sodium channels slam shut, and the cell returns back to its polarized state. It goes back to rest. Actually, it goes back to rest in an accelerated way because we've got extra potassium channels, potassium rectifier channels they're called, opening here to really push out lots of potassium in the cell and very quickly repolarizes. And this whole thing takes 1 millisecond. Okay, so a neuron can do this up to 1,000 times a second. So the way neurons that spike, that produce action potentials or impulses, transmit signals is by deciding millisecond for millisecond whether or not they're going to fire an impulse. Right? And they're going to decide that simply by deciding whether the place where they have these sodium channels, the polarity is sufficiently, whether the cell is sufficiently depolarized. So if you've got a neuron, the way it really, the thing about these sodium channels is that they all sit in the neuron's axon, all right, because that's where the neuron is going to produce its decision as to whether it wants to fire an impulse or not. So you get currents coming in through the dendrites, all right. They get passively conducted. I let a sodium ion in, all right. It'll travel into the, go into the dendrite. It'll flow through the dendrite. And it'll depolarize the membrane here, and if it depolarizes the membrane here just enough for my sodium channels, my voltage-gated sodium channels to open, then I'll get a nerve impulse that travels along the axon. Okay. So every millisecond of your life, all the neurons in your brain will decide whether the amount of current that's been injected into them through the dendrites by the other neurons or by sensory stimuli in the outside world are enough to cause them to fire an impulse. All right, and if it has, then the impulse will travel along there. All right. Now, how do we know all this? This is kind of in the interest of time, I'm not going to say an awful lot about this. Actually, the way people work this out, how this all works with these channels, is by working with huge axons in squid. All right, people got Hodgkin and Huxley found out that squids actually have axons that are so big that you can stick a whole pipette inside them and change the ions inside and outside and inject currents, and it's another story which I'll be told another time. I'm aware of the fact that we're running low on time, but the thing is really, if you inject if you inject currents into a neuron at some low level, they may not spike at all, because you're not depolarizing the membrane enough for the sodium channels to open. You don't go to the threshold potential of these sodium channels, which is in the order of 30 to 50 millivolts or so. All right. If you inject more current, they'll fire. All right. They get the sodium channels, voltage-gated sodium channels open, the cell depolarizes. Potassium rectifier channels open, the cell repolarizes. But then you keep injecting more current and it depolarizes again. All right. So like this, I get a firing rate, a regular firing of impulses that gets faster and faster if I inject more and more current, because I'll go through, I'll depolarize enough to get the next impulse going faster. So I have a rate code. Okay, so neurons will represent the world around them by firing impulses at a high rate or at a low rate. Okay, that's how they transmit the information down these channels. All right, but they can only do this. They can only fire a maximum of 1,000 spikes a second. In fact, most neurons will never fire more than 400 spikes a second. All right, so that if you can say, look, at any one moment I fire or don't fire, people in information technology would call that 1 bit of information. All right, so the maximum bit rate of a neuron is a few hundred bit, which isn't an awful lot. If you look at specifications for a USB cable or something, you'll see it'll be many megabits per second. So your USB cable can carry as much information as your optic nerve, which has got over 1 million axons that all decide whether they're going to fire or not. Okay, so actually your eyes and your optic nerve, and this is something we're going to talk about 2 lectures from now, are quite a miracle of engineering, how much information they can squeeze down a cable that's actually not a very good cable. All right. Neurons are not very good cables, but they're very energy efficient cables. They can basically shove a lot of information around without taking up, if you were to try and simulate all this in a computer, you'd need a power station to power a computer that simulates just a single human brain. All right, huge, and so they can do this in a very efficient way. Now, one thing that is perhaps a little bit more advanced is to sort of say, look, I told you that basically, if you fire it, if you drive a neuron very hard, it'll fire very fast, and if you drive it less hard, it won't fire quite so hard. But the thing is, actually, some neurons can fire very complicated patterns of activity. If you drive them quite hard, they don't go drrrr, but they may go vrr, 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 vrr. And this is because they have all sorts of complicated channels that will, let calcium in, which then activates some other channels through some complicated system and so on. We'll take more about that at some other time. So that's kind of curious. And another thing that's very curious, and we might be able to talk about that a little bit, is that, of course, this is about firing codes. These are classic recordings by a guy called Adrian, who worked on stretch receptors that he took out of frogs, okay, and he just recorded from the neurons, pulled on the frog muscle, and if you suddenly pull on the muscle, the nerve will suddenly start firing, and the more you pull, the faster it fires. But interestingly here, he then maintained the tension, and the neuron did not maintain its firing rate. It suddenly actually had slowed down. Okay, this is something known as adaptation. And adaptation is kind of cool because it's responsible for all sorts of curious effects, like after images on your retina. If you stare into the bright light, you close your eyes, you have a sort of an inverse image of what you last saw. These things are due to adaptation, because if you imagine you've got say, another example of adaptation, your hands are really cold, you put them under an average water tap, the water will feel really hot. Well, why is that? Because you've got cold receptors and hot receptors in your hands. Normally they fire both at average rates to say, well, we're neither terribly hot nor terribly cold. Now your hand goes very cold, all right? Your cold receptors will initially fire a lot. When you first immerse yourself in cold water, they fire like a lot, but once you stay in the cold water for a while, they adapt. It doesn't feel so cold anymore. Now you go into, you go from the cold water into tepid water. The cold receptors are all adapted, so they're firing at a very low rate, but your hot receptors now fire at a medium rate, and the balance between them makes it look as if it was very hot, whereas in reality it isn't. Okay, so adaptation is a phenomenon that gives rise to all sorts of interesting illusions, including, for example, we'll do that. We'll do that another day. I'll show you after effect illusions like the waterfall illusion, which are visual demonstrations of adaptation, which are really rather cool. So we've got a spike code, okay, which has to encode all sorts of things. It's normally a rate code, but it's a little bit complicated because there's adaptation, and because some neurons like to burst and fire in bursts, and so on. One last thing that's kind of perhaps useful to be aware of is that axons, where these spikes are transmitted, they are often covered in a little cover that's known as the myelin sheath. All right, the myelin sheath. So you've got little cells, glial cells that wrap themselves around the axon to give extra insulation, and that helps actually for these action potentials to travel very, very quickly. But there are certain diseases where the myelin sheath gets attacked. Okay, it can get broken down, for example, by autoimmune diseases like multiple sclerosis. And what happens then is that these, that suddenly the impulses are no longer transmitted in a very effective way. So what happens? Well, you can get all sorts of problems. I mean, if you have for example, if you have a demyelination of your motor neurons, you will send very fast impulses down the axon in order to try and contract your muscle very hard, but your muscle is just not going to hear it. All right. So you really have, so demyelination is often a problem. Also, I mentioned earlier white matter, all right, in the brain. We've got grey matter and white matter. White matter is all these axons which send all those impulses over long distances, from one part of the brain to another. This is actually white because of the myelin content. The myelin is like little fat droplets, all right, that lines these axons here, and therefore it makes white matter white, just like milk is white or butter is white, because you've got little fat droplets that scatters the light. All right, and that's really what I wanted to say today, which is far more than enough. So what I think I'm going to do now is first of all give all of those of you who need to rush off a chance to rush off, and those of you who want to stay on a little bit longer and do a little Q&A and talk maybe a little bit more about brain anatomy, about anything like this, can stay. God, you guys must be having a good time if nobody's running off and stuff.